Hello, in this video we're going to take a look at how to create and solve partial fractions. Okay, partial fractions is when you separate a fraction like we have over here, when we separate that into two or more simpler fractions. In this video we're going to look at one with linear factors and one with quadratic factors. Now when you're doing partial fractions, there's four general steps. The first thing you do is check if the degree of the numerator is smaller than the degree of the denominator. So that needs to be the case if we proceed with our partial fraction decomposition. Now, if that's not the case and the degree of the numerator is bigger than the denominator, then we have to perform polynomial long division where we take the top and divide by the bottom. We're not going to cover that in this video, but you would do that division and then proceed with the partial fraction decomposition on the remainder of that division. Now after you check that, real quick check, you then factor the denominator, because the factors that are left over are what you're going to split it up into two fractions with. Now you write the partial fraction decomposition. If the factors are linear, it's going to be of the form a over the linear factor. We will call this x plus a sub 1 plus b over x plus a sub 2. So I'm just talking about linear factors where the degree of the factor in the denominator has an exponent of 1. And this process would continue for as many factors as you have. If it's quadratic, if the factor is quadratic and you can't break it down any further, then it's going to be of the form ax plus b in the numerator divided by your quadratic factor, whatever that is. And this process would also continue for as many quadratic factors as you have. And the quadratic factor can be of this form too, x squared plus the constant, just so long as the highest degree is 2. And then step 4 is to find the coefficients. And this is where most of the math work happens. That's to find the a, b, c of the variables that we set up. Okay, that's the general process. Let's try and solve this. This first one is a pretty straightforward one. So the degree of the numerator is 1, degree of the denominator is 2. So yes, that works. So now we factor the denominator, and we go x minus 2 over x plus 3 times x plus 1, because two things that multiply to 3 and add to 4. Okay, we got it. Now, are the factors linear? Yes, they are. So we write the partial fraction decomposition of a over the first factor plus b over the second factor. And those are the only two factors we have, so we stop there. Now we've got to find the coefficients. To do that, here's the kind of the math of it. We multiply both sides by our LCD, which is this. So basically you multiply by the denominator of the original. So I'm multiplying the left by it, and I'm multiplying the right side. On this side, everything cancels, leaving me just x minus 2. On this side, when this distributes to this one, notice how the x plus 3's cancel out, leaving me a times x plus 1. But now, once I distribute this to the b, this time it's the turn for x plus 1 to cancel, giving me b times x plus 3. This right here is what they like to call the basic equation, just a fancy name for it. Now we need to solve this basic equation. We need to find what a and b are. You rely on the idea that this equation right here, that I circle in yellow, that's true for every value of x. It's some statement that's true for every value of x, but only one value of a, one value of b. So it works for every single x that we can imagine. So we're going to let x equal something that will give us an advantage. Notice how if I let x equal -1, when I plug that in here, it's going to give a times 0, which eliminates the a, giving me just one variable, b, to solve for. Look what happens. So I plug in -1 for x, so I get -1 minus 2 equals a times 0 plus b times -1 plus 3, giving me -3 equals b times -2. Let me change that to a positive 2. -1 plus 3 is positive 2. And then I can divide by 2. Divide by 2. So b is equal to -3 halves. Okay, so that's one answer. Now I go through a second time, and I let x equal a different number, this time to help me solve for a. Well, if I let x equal -3, I think you can see what happens. I now have -3 minus 2 equals a times -3 plus 1 plus b times 0. So the b is eliminated, giving me -5 equals a times -2. Divide by -2, and I have a equals 5 halves. Okay, so I found my two coefficients. I guess I could add a step 5 onto this. Write the partial fractions. I suppose it's good to write your final answer. So we take our coefficients and we just stack them. And I'm going to write this way up at the top. We stack them on top of our factors. So this original fraction now equals 5 divided by 2 over x plus 3 plus -3 halves over x plus 1. That's the easy way to write it, but perhaps a better way is to say that 5 halves is 5 over 2 times the x plus 3 factor. The -3 halves would create a subtraction here, and we can drop down the 3 halves like this. And there's the partial fraction decomposition with linear factors. Now let's go over and try quadratic. Okay, let's try this partial fraction decomposition. So, is the degree of the numerator less than the denominator? Yes, 2 to 4. Okay, so let's try and factor the denominator. So on the top I have 2x squared plus x plus 8. But on the bottom, this is a quadratic form. Okay, so it's x to the 4th, x squared plus 16. So I can still look for two factors of 16 that add to 8, which would be 4 and 4. It's just in this case, I have x squared plus 4 times x squared plus 4 instead of just x plus 4. And that's because this is x to the 4th and x squared. Okay, what do you notice? We have two quadratic factors. So this is going to split up into ax plus b over the first factor plus cx plus d over the second factor. But wait 1 second. Notice how I have a repeated factor right here and here. This is another special rule with partial fractions. If you have a factor that's repeated, the next time I write it, the second time I write it, in my basic equation over here, it's going to be squared. And if there was a third repeated factor, so perhaps in a different problem, I would ex plus f, and I would write x squared plus 4 to the third power. So every time you write it again, you have to raise the power of it as well. Okay, so we don't have that in this one. So now here we go. Now we try and find the coefficients. So I create my basic equation, multiply both sides by x squared plus 4 squared. That eliminates on the left side. Now over here, I can write what I'm doing, x squared plus 4 squared. When I distribute this to the first one, I have ax plus b, and only one of the x squared plus 4 is canceled, giving me that. On the second one, both of them cancel out, giving me just cx plus d. All right, now to solve this. Using our method of the previous example, if I let x equal some number, it's not going to help me too much. I can let x equal 0. That would eliminate the a, but then I'd have b times this, b times 4. The c would be gone, but I'd still have the d. So I'd still have b and d in there, so like two variables, so it'd still be hard to solve for. okay, I could try and get this factor to be 0 because that would eliminate both of those. But the only way to make that 0 would be if I do negative 2i. So I can't really let x equal some number to eliminate anything. So it seems like I'm stuck. But we can actually use system of equations and something called equating the coefficients. And I really like this. I think it's pretty neat. What we're going to do is we're going to distribute on the right side. Okay, so I have a little FOIL here. So I have ax cubed plus 4ax plus bx squared plus 4b. Nothing to distribute on the other side, so that makes it a little easier. It's just cx plus d. Now I'm going to rearrange these in order of the coefficient. In order of the power. So we're going to say ax cubed plus bx squared plus, now I have two x's, so 4ax plus cx, and then my constants, 4b plus d. Now the only way for this whole equation to be true is if I have 2 for all of my x squareds. So that means this has to equal 2x squared. Well, notice how I have only one x, so everything on the right side that equals x has to add up to 1. Notice how I have 8 for a constant. That means everything on the right side that's a constant has to add up to 8. And what about this x cubed? Well, there's 0x cubed, so this has to add up to 0. What that is saying is I'm kind of creating a system in my head. I'm saying that every coefficient that adds up to x cubed has to equal 0. Everything that has an exponent of x squared, which is just b, has to equal 2. Everything that has a variable of x has to add up to 1. So 4a plus c has to equal 1. And then finally, my constant of 8, everything that is a constant, 4b plus d, must equal 8. And creates this system of equations here. Now this is a very easy one to solve because 2 of the variables are already solved for. I know that a equals 0, b equals 2. So I'll even write that. A equals 0, b equals 2. So it is really easy to solve this system, but it is a system nonetheless, which means if it was more difficult, I could use my techniques of like eliminating variables out of this equation and this one by adding together and multiplying the equations, as you should know to do when solving a system. But in this case, I can use simpler methods. This would become 4 times 0 plus c equals 1. So c is equal to 1. And then this one, 4 times 8 plus d equals, b is 2. So 4 times 2 plus d equals 8. 8 plus d equals 8. And as you might see, that means d is 0. So there are all my coefficients. Last thing to do is just put it together in our final answer. So we'll go back up here, and I'll take this guy. ax plus b. A is 0, b is 2, so this is 2 over x squared plus 4 plus cx plus d. Well, c is 1, so 1x, d is 0. So I say x squared plus 4 squared. That would be our final partial fraction decomposition.